In his video about trees, Veritasium mentions the idea of negative pressure to explain how trees are able to be taller than 10 meters. But after watching the video, I still didn't really understand what negative pressure is. I tried to look up more online, but there was little to no information available. So I did some thinking, and I feel like I have a better grasp of it now. I'll try to explain things. First, let's recap. It turns out that there is a limit to how high water can be sucked up a tube. This comes from the fact that the pressure in a fluid is equal to rho times g times h, where rho is equal to the density of the fluid, g is the strength of gravity, and h is the height difference between the 2 points. If you plug in 1 atmosphere of pressure difference, the density of water, and the strength of gravity, you get a height of 10.3 meters. But this formula can be extended beyond this. So if we have a continuous water column that is more than 10 meters tall, there's gravity pulling down on it, but there's also some upward force canceling it. In the case of trees, it was mentioned that this supporting force is caused by the meniscus, or the surface tension at the meniscus rather. And so the tree actually does have valves. Water can evaporate out of the meniscus, but the surface tension prevents it from falling in. This balancing of forces is exactly the same as with hydrostatic equilibrium. And you can just apply the same formula. If h is greater than 10 meters, then that means that delta P must also be greater than 1 atmosphere. And so pressures just go negative. There's nothing too special about it. So in this case, the water at the top of this tube, which is also greater than 15 meters, is being pulled downwards in this direction and in this direction, but there's no net force. But the reason the water doesn't just split is that there's a sort of cohesive force between the molecules themselves. So as Veritasium mentioned, you can think of the negative pressure as kind of like tension in a string.
A siphon works because of gravity. The water is essentially falling out of a very weirdly shaped hole. The water will continue to flow until the hole is brought above the water level, or until the water levels of each of the reservoirs reach the same height. Lifting the hose up increases the height of the water in the hose. This change in height decreases the hydrostatic pressure of the water in the hose. The work required to cause this decrease in pressure is the work done when you overcome gravity to lift up the tube.
Yep. Keep going and see if it stops working.
Yeah, I think that just did it.
There's still water here. So still. Let's see, this might break it right here. No, still going. Still going.
Yeah, see now it's...
Now it broke. So we saw bubbles form spontaneously in our siphon, but we don't know what kind of gas it is. It could be water vapor, or it could be nitrogen and oxygen. I suspect that the decrease in pressure near the top of the siphon means that the gases dissolved in it become supersaturated and spontaneously fall out of solution. You've seen this whenever you open a bottle of soda. The pressure goes down, causing the gas to become less soluble, and so the now supersaturated solution forms bubbles. It's also the cause of decompression sickness, or the bends, in scuba divers, where nitrogen that dissolved into the blood under high pressures forms bubbles inside the blood vessels as the diver ascends and the pressure drops. Okay, so one of the things I found interesting was that our siphon still sort of worked even after the bubbles formed in it. So we've got a bubble in right here, and if I raise this jar, that bubble moves. But if I lower it a little, like, okay, right here, the level of this jar is higher than the level of the other jar. So water should be flowing. If you look, you might see that the water is flowing slowly. And then if I change the height further, that bubble will just get pushed out. But if you get a large enough bubble, let's get them to join forces. Alright, large enough bubble, this doesn't really work. Here I can do this and nothing happens. But then if I get this tilted a bit, I can push that bubble right out. But that requires lifting the jar a lot.